Welcome dear learners. We are continuing Unit 1, Chemistry as a Science Discipline and Scientific Analysis. The present module is intended to discuss correction of determinate errors in analysis. The contents of this module are determinate and indeterminate errors, type of determinate errors such as instrumental errors, method errors and personal errors, strategies for correcting determinate errors, and problems based on various kind of errors. First of all, we are discussing type of errors. This part I am included in this discussion only as a revision. In the previous module, we learned some basic aspects of various kinds of errors. You know the fact that an error is the deviation of true value and the experimental value, or the difference between true value and the experimental value is termed as error. Error is universally related to accuracy. Higher the accuracy, lower will be the error and vice versa. It is possible to express error as absolute error and relative error. You know there are two important type of errors and the basics of that. Now we are just revise the concept and enter into more details of different type of errors. First of all, chemical analysis are affected by at least two different type of errors. What are these two different type of errors? You can just remember that the two type of errors are, first one, systematic error, and it has a synonym that is nothing but determinate error. The second category of error is random error. It is otherwise known as indeterminate error. From the names itself, it is very well clear that the first category, determinate error, the source of which are known, it has an assignable cause, and it is possible to minimize or rectify systematic errors. However, for random errors, there is no clear-cut source for the random errors. Even though there are sources, it is not possible to exactly locate the correct source of the random error. Moreover, it is not possible to exactly rectify the random error when compared with the systematic errors. Now, in addition to these two kind of errors, you are also familiar with the third type of error, that is nothing but gross error. Thus, in analysis, especially in quantitative chemical analysis, three kinds of errors are there. The first one, systematic error or determinate error. The second category, random error or indeterminate error. And the final category, that is nothing but the gross error. These three kind of errors definitely affect the true value and its connection with the experimental value. That is, these kind of errors will cause the result which are not trustworthy. So, we will not get any accurate value during a measurement if these kind of errors are involved in the measurement. Now, systematic error, as the name indicate, causes the mean of data set to differ from the accepted value. Random error causes the data to be scattered more or less symmetrically around the mean value. So, this is a major difference between random error and systematic error. In the case of the random error, there is an error distribution. There is a centralized value and some values are scattered or distributed randomly about a central value. That is a peculiarity of the random error. And in the case of gross error is definitely differ from the previous two kind of errors, that is the indeterminate error and determinate error. That's why the gross error exists as a special category. It is the third type of error that may occur in quantitative analysis. So, the gross error usually occur very occasionally or only occasionally, are often large and may cause a result to be either high or low. This is the peculiarity of the gross error. That means, more clearly speaking, gross error leads it to higher values from the true value as well as lower value from the true values. So, gross error can increase or decrease a measuremental value, a measured value from the true value. Now, more details about the gross error. These gross error are often the product of human errors. What do you mean by the term human errors? We, the pupils, which are interested in analysis, or an analyst will generally perform several kind of analysis. The person's bias, the person's inconsistency, disability, several kind of troubles as personal defects may affect the analysis. Such kind of errors, the errors may due to some carelessness also. So, the errors produced by the analyst himself is known as the human error. The gross error can be considered as the product of various kind of human errors. Moreover, gross errors lead to outliers. Outliers, results which appear to be different markedly from all other data in a set of replicate measurements. Suppose we are performing a volumetric analysis. During the volumetric analysis, we will get a different titer values such as 20, 20.1, 20.2, 19.9, etc. And in addition to these precise values, suppose we got a high value of 25 or a very low value of 15. These two values can be considered as outliers in a measurement. These outliers are the indicate the existence of gross error. So, gross error may lead to the formation of values which are markedly different from the existing set of values, or we can simply say that gross error leads it to outliers. Now, we are giving emphasis to determinate errors. We know previously some basic aspects about determinate errors. First of all, determinate errors are also known as the systematic errors, and these errors can have a specific cause, and to some extent these kind of determinate errors can be identified as well as corrected. It should be noted that it is not possible to eradicate all kind of errors from an analysis. So, more or less, it is easy to reduce the magnitude of determinate errors compared to indeterminate errors. That is the advantage of determinate errors. Now, the determinate errors have same magnitude for replicate measurements made in the same way. Suppose we are doing a conductometric titration, that is a titration where we are measuring the conductance. If you are using same instrument for doing the conductometric titration, in repeated experiments, the magnitude of the determinate error is constant throughout the experiments with the same instrument. Now, these determinate errors may lead to bias in measurement result. That is the important implication of the determinate error. Now, important characteristic features or characteristics of the determinate errors. The first feature is its reproducibility. The determinate errors are reproducible. They occur in a predictable manner during repeated experiments. Suppose, as I mentioned in the case of the just previous example, that is conductometric titration, if you are doing repeat titration by using same instrument under same condition, these errors repeat in every case. That is, the determinate errors are reproducible. The second characteristic feature is bias in results. The determinate errors cause the measured value to deviate systematically from the true value. That is, it leads to bias in analytical results. Now, the third characteristic feature is correctable nature of the determinate error. As I mentioned earlier, it is possible to correct to a greater extent the determinate errors. That is, determinate errors can be identified and corrected. Not in full measure, but substantially you can correct the determinate errors. Once identified, these errors that are determinate errors can often be eliminated or minimized. Now, type of determinate errors. We familiarized with the three kind of determinate errors. We can just remember what are various kind of determinate errors. As you know, the determinate errors are three types. The first category is instrumental error. Instrumental error is due to the wrong performance of the instrument under our consideration. The second category is method error. It is otherwise called error due to method. If you are following a non-trustworthy method for analysis, it may lead to the generation of method errors. And the last category of determinate error is the personal error. The personal error is a human error, that is the mispractice under certain conditions may lead to the personal errors. The first category, instrumental errors, we are considering in more detail. Instrumental errors are caused by non-ideal instrument behavior, by faulty calibration, or by use under inappropriate conditions. There are several instruments we are using in analytical chemistry laboratory. pH meter is a good example. Conductometric titration setup is another example. Potentiometer and potentiometric titration setup is another example. There are so many instruments we are using in analytical chemistry, analytical laboratory. Even there are so many spectroscopic methods also. There are photoluminescence spectroscopy, NMR spectroscopy, ESR spectroscopy, many instruments we come across with the analytical laboratory or with an analytical laboratory. And if you are using an instrument which is not perfectly calibrated, calibration means you have to take a reading, you have to fix the reading of the instrument with reference to some standard. That procedure is known as calibration. If there is no proper calibration, the instrument will give wrong values during taking of the measurement. Moreover, the instrument can be placed under inappropriate conditions. Especially inappropriate condition implies the temperature fluctuation, the voltage fluctuation, etc. These two fluctuations definitely affect the performance of an instrument and may lead to instrumental errors. So, pipettes, burettes, volumetric flask, etc. all these things are associated with volumetric analysis, which is an important classical quantitative analysis. Pipettes, burettes and volumetric flask may hold or deliver volumes slightly different from those indicated by their graduations. So, suppose a 20 ml pipette may sometimes deliver 19.9 ml of the liquid. In certain other cases, the delivered volume may be higher than 20 ml. This kind of error can be considered as instrumental error. Calibration, however, eliminates most systematic errors of this type. That is the advantage of instrumental error. We can locate the error and we can calibrate the instrument, and proper calibration of the instrument can eradicate to better extent the instrumental error. Now, electronic instruments can be influenced by noise, temperature, variation in the pH, and are also subjected to these type of instrumental errors. Errors of this type usually are detectable and correctable. That is the advantage. Now, we are discussing the second type of determinate error. The second type of determinate error is nothing but error due to method or method errors. We can just remember what is the reason for the method error. The non-ideal chemical or physical behavior of the reagents and the reactions on which an analysis is based often introduce systematic method errors. So, method errors or error due to method are systematic errors or determinate errors, and this may due to non-ideal chemical or physical behavior of the reagent and reactions. Such sources of non-ideality can be discussed here, can be considered here. Such non-ideality that may lead to method errors include the slowness of some reactions. Certain reactions whenever we are measuring some rate of the reaction or some data associated with some reaction, whenever we are taking such data, if a reaction is abnormally slow, the result may be erroneous. So, the slowness of some reactions, some selected reactions is a non-ideality. Next one, the incompleteness of some other reaction. Certain reactions will not complete, so that reactions may lead to method errors. The instability of some species during the transformation of reactants to products. Some of the products may be highly unstable and you cannot measure its concentration exactly. In such a case, method error may occur. The lack of specificity of some reagents. This is mainly associated with organic transformations and reactions. There are several reagents which are not specific. Not specific means they will not attack to a particular position of an organic molecule like that. So, lack of specificity of reagents may lead to method errors. And finally, the non-ideality include the possible occurrence of side reactions. So, side reactions lead to the formation of side products. That side products may influence the original analysis and that lead to method errors. So, by this, these 5 important non-ideality are the ultimate source of method errors. Now, errors inherent in a method are often difficult to detect, and hence these method errors are usually most difficult to identify and correct. In the last module, whenever we discussed about the 3 kinds of determinate errors, I mentioned the important fact that method errors are the only type of determinate errors which are difficult to identify and difficult to correct. However, the personal error and instrumental error can be comparatively easily corrected. The best way to eliminate the bias of an analytical method is by analyzing standard reference material or by calibrating using standard reference material, which are abbreviated as SRMs. Now, we are considering the third type of determinate error. The third type of determinate error is nothing but the personal error. The personal error results from carelessness, inattention or personal limitations of the experimenter or analyst. These kind of drawbacks which may occur from the side of the analyst may lead to human error or personal error. Many instruments require personal judgments. If the analyst is failed to perfectly measure, perfectly judge the analytical values obtained from that instrument, that may lead to erroneous result and hence the personal errors may occur. Examples of personal errors are shown here. It include estimating the position of a pointer between 2 scale divisions. Whenever we are taking some readings, suppose there is a point that is between 2 divisions, 2 scale divisions, and we are going to read the exact division or read the exact value. In such a case, the personal error may occur. The color of a solution at the end point in a titration. You know the fact that the end point of a volumetric analysis or volumetric reaction or titration is generally noticed by a color change. For example, In acidometry and alkalimetry, you are using indicators, acid-base indicators like phenolphthalein, methyl orange, etc. The color change should be noted, and the color change is marked as the end point of the reaction. Whenever you are noticing the color change of an indicator in a particular volumetric reaction, if you failed to make a proper judgment, it may lead to personal error. The level of a liquid with respect to graduation in a pipette or burette. The graduation in a pipette or burette you can see with the help of your naked eye, and if you fail to judge this graduation correctly, the reading you took may vary from the original value, and that may lead to personal error. So, all these categories, all these are nice examples for personal error that may happen from the side of the analyst himself whenever he performs the analysis, the quantitative chemical analysis. Now, judgment of this type often subjected to systematic unidirectional errors. A universal source of personal error is prejudice or bias. You have to note this point. Prejudice or bias is the universal source of personal error. Number bias is another possibility, is another source of personal error that varies considerably from person to person. The most frequent number bias encountered in estimating the position of a needle on a scale involves a preference for the digit 0 and 5. Whenever you are taking the position of the needle as the reading, then if you are not properly judging that, the number bias may be there, and the number bias leads to personal errors. Also common is a prejudice favoring small digits over large and even numbers over odd. This kind of prejudice may also lead to number bias, which again lead to personal errors. Digital and computer displays on pH meters, laboratory balances and other electronic instruments eliminate number bias because an analyst need not take reading because this instrument directly give the values of the analysis. Now we are looking on to indeterminate errors. These are second type of error. Determinate error, indeterminate error and gross error are the three probable kind of errors that may occur during quantitative chemical analysis, out of which we have discussed the gross errors and determinate errors, and there is one more category is remaining, that is nothing but indeterminate errors. Indeterminate errors are also known as the random errors. These are errors from unpredictable and uncontrollable variations in experimental conditions or measurement process. These errors cause measurements to fluctuate randomly around the true value and cannot be completely eliminated, but you can only minimize that. These errors do not follow a consistent pattern or a trend. They can cause, the indeterminate errors can cause measurements to be higher or lower than the true value. Now, characteristic features of indeterminate errors are shown here. First one, these kind of determinate errors are non-reproducible. We learned that determinate errors are reproducible. However, indeterminate errors are non-reproducible. They vary in magnitude and direction in each trial. Sometimes this indeterminate error may lead to higher experimental value, in some other case lower experimental value, so on and so. So, it is a direction, it is a magnitude, etc. cannot be predicted and they are non-reproducible. Unavoidable. Indeterminate errors are unavoidable. It is not possible to completely rectify the indeterminate errors. Follow a statistical distribution. This is very, very important as far as the expression of errors in statistics is concerned, these errors often follow a normal distribution when many measurements are taken. The normal distribution in statistics is otherwise called Gaussian distribution. So, these indeterminate errors follow a Gaussian distribution or normal distribution when analyzed them statistically. Now, the question arises, how to minimize indeterminate errors? We have to minimize determinate errors also, the procedure for which we will consider in coming slides. Prior to that, we are now considering the minimization of indeterminate errors. While indeterminate errors cannot be completely avoided, their effects can be reduced by some methods, and these methods include repeating the measurements. You can take repeat measurements using same instrument many times. Improving instrument quality, you can calibrate the instrument, you can service the instrument like that. Controlling environmental conditions like pH, temperature, voltage fluctuations, etc. You have to use a training person or a trained analyst to take a reading. These are various options, not to completely eradicate the indeterminate error, but to minimize the indeterminate errors. Now, we are considering the strategies for correcting determinate errors, or we are discussing various methods for the correction of the determinate errors. The strategies, several methods are there. Eliminating determinate error is a critical step to improve accuracy of analytical measurements, because error is inversely related to accuracy. Therefore, it is essential to remove or eradicate or to minimize these determinate errors. Since these errors have identifiable causes, they can often be minimized or corrected. Calibration is a good method to reduce the instrumental error. We have to first focus how to correct instrumental errors. The method calibration is a good alternate. Another correcting method for instrumental error is maintenance. Perform regular maintenance and servicing of the equipment with which you are taking the measurement. Now, replacement. You have to replace outdated instruments with the newer, more reliable models. This is a good alternate to reduce the instrumental error. Now, verification. You can cross-check the result with different instrument or method to ensure the consistency. That is, you can use electronic balance to take weight of a sample. You have to measure this weight in different instruments to check their consistency in the value. Now, correcting of method errors. I just mentioned the fact that method errors or error due to method are very difficult to identify and correct. Even though this is a situation, there are some methods. Validation of methods. Ensure the analytical method is validated for accuracy, precision and specificity before its use. Reagent purity. You can ensure the purity of the reagent before starting the analysis. That is, use high purity reagents and solvents to minimize contamination or probable side reactions. By using reagents of high purity, you can minimize method errors to a good extent. Optimize procedures is another chance, another way to reduce the or correcting the method errors. Review and refine experimental procedures to eliminate biases. Use of blank solution. Run blank samples to account for the interferences and correct for background signals whenever you are taking instrumental readings especially whenever you are taking spectroscopic measurements such as UV visible spectroscopy, etc. The last part is correction of personal errors. How to correct the personal errors? Double checking is a good alternate. You can have critical measurements reviewed by a second person. That is, the analysis performed by one analyst can be repeated by another person and you can double check the values. Automation. Use automated systems to reduce operational errors. The operational errors or personal errors is caused by the analyst. So, if you replace analyst with some automated instruments, you can reduce this personal error to a good extent. Now, training. Provide adequate training to analysts on proper laboratory techniques and equipment use. So, before starting usage of high-end instruments or an analytical instrument, the person who is responsible for using or handling that instrument must get proper training on the procedures and the techniques behind that instrument. Standard operation procedure, abbreviated as SOP, develop and follow detailed standard operating procedures to reduce variability in the procedure. So, adopt a standardized procedure, and by using some standard operating procedure, you can minimize the personal error to a good extent. Now, as the last part of the discussion, we can have some problems based on the topics we have covered yet. So, moving on to the first problem. Which of the following is an example of a determinate error? These are the options: fluctuations in temperature during an experiment, impurities in a reagent, random noise in an instrument, variation in readings due to operator fatigue. The exact answer, most appropriate answer is impurities in a reagent. Impurities in a reagent directly lead to method errors, which is a determinate error. So, your answer is B, impurities in a reagent. Now, the second question, which of the following steps can help minimize determinate errors? These are the options: taking multiple measurements, calibrating instruments regularly, averaging repeated measurements, using statistical methods. On careful analysis of these options, we can arrive at the conclusion that option B, that is calibrating instruments regularly, can reduce or minimize determinate errors. So, option B, calibrating instruments regularly, is the most appropriate answer to this MCQ. Next question is here: what is the primary effect of determinate errors on measurements? These are the options: decrease in accuracy, decrease in precision, increase in randomness, increase in standard deviation. It is very simple question and you can arrive answer directly. Option A, decrease in accuracy. You know the fact that accuracy is inversely related to errors. Higher the error, whether it is determinate or indeterminate, there will be a direct decrease in accuracy. So, option A is the answer. Now, the next question, an indeterminate error can occur due to. The options are faulty instrument calibration, fluctuation in environmental conditions, systematic procedural flaws, misreading a scale consistently. Indeterminate error is the question. From this choice, you can arrive at the conclusion that option B, that is fluctuations in environmental conditions. Environmental conditions such as the temperature fluctuation, voltage fluctuation, pH variation, etc. may lead to indeterminate errors. So, your answer is option B. Now, next question. A volumetric flask reads 100.2 ml instead of the true value of 100 ml. The question is about the percentage error. What is the percentage error? Options are here: 0.2 percentage, 0.5 percentage, 0.1 percentage, 1 percentage, etc. How to calculate the percentage error? First, you take the difference between true value and the experimental value, take its modulus. That is nothing but the error which is called absolute error. Divide absolute error with the true value and multiply with the 100. You will get the answer to this problem. It is clear that the answer is 0.2 because percentage error is calculated using this expression. 100.2 minus 100 divided by 100 multiply with the 100. So, the result is 0.2. Thus, we have discussed various kind of errors and the different ways to minimize or rectify the errors. That all about the presentation. Have a nice learning experience. Thank you.